Okay. So we've already talked a little bit about this problem. We want to find the minimum distance, x, to keep the bar or platform in equilibrium. So the easiest thing to do is to draw a free body diagram for the platform. I'll do that first. So here's the platform. We're going to have a tension force acting up. I guess it's occurring at A, so we'll call it tension in A. And there's a tension force at B. And then there is a 20 Newton, not a very large force, but a 20 Newton force acting at some distance x from point A. So there's your free body diagram. So how should we solve this problem? Well, there's two unknowns, TA and TB. Summing forces in the x direction won't give us a whole lot, will it? So we'll probably need to sum moments. And just because of the way the unit is given here, oh, I forgot, this thing is 1 meter. It'd probably be easier to sum moments about A, since the problem variable x is referenced from A. So let's sum the moments about A. So I'll have the moment caused by the 20 Newton force about A. That's going to create negative moment and have a value of 20x. Positive moment at B with a moment arm of 1. So it looks like the force in B is going to be what? 20x, right? So that's two unknowns, but still that's a pretty easy relationship. So now I can sum forces in the y direction. Oop, forgot to put F in there. So starting from the left, I have the tension force acting up at A, the tension force at B acting up, and then I have my load 20 newtons acting down. So I got two equations and I've got 1, 2, 3 unknowns. I need something else. What else do I need? Well, what's going to happen to the force TA as it goes up over the pulley C? Does it change? No. It does not. So let's look at a free body diagram of the peg. So here's the peg at D. So I should have my force TA here, and I should have my force TB there. So I should be able to generate another relationship, right? Now, which way is this thing going to move? The way the problem stated. I'm trying to find the minimum x, so as I move closer, my load closer to A, it's more likely that A will start to slip and go down. So really the general motion of my cable in this case is this way, right? So the resulting friction force would be in this direction. So that means that TB so that means that, is that right? Yeah. So TB plus the friction force will give me TA. Right? So that means that TA should be equal to TB times E. Let's see, what's the coefficient of friction over the peg? 0.03? Or 0.3, I'm sorry. And then what's the contact angle?
Pi over 2.
It's quarter. Yeah, pi over 2. Bless you.
Thanks.
So all this is going to tell me is that TA is going to be equal to whatever that is. Somebody compute that real quick. E to the 0.3 pi over 2. It's going to be greater than 1 probably.
.60.
That sounds reasonable. If I look at it carefully, I've got 1, 2, 3 equations. So with this relationship here, I can put it in there and solve for TB. Once I know TB, I can get X. So let's see if we can do that real quick. So if I take equation 2, and it says TA, which I know TA is 1.60 TB plus TB should be equal to 20 newtons. So what's TB? It looks like it's 20 divided by 2.6. 7.69? And then once I know TB, I can put that back into equation 1. And that equation says that X is equal to TB divided by 20. So divide that by 20. I got 0.385. And that would be meters. If I get 38 centimeters too close to A, it's going to start going down. Now what if I wanted to find the maximum value of X I wanted to go to? What would change? Well, this part of the problem would be unchanged, right? What would change would be here. Now the motion would be down. This relationship would flip, and I'd probably get a much larger number. Hopefully not greater than 1. Well, I mean, that'd be safe if it was greater than 1. That means I could stay on the platform and it wouldn't move. You want to see that solution? Let me grab another piece of paper so I can kind of cover up what we've done. So what, instead of finding the minimum value, I wanted to find the maximum value. So again, there's my peg at D. I still have my tension force at A and my tension force at B. Except now, as I move towards the right side, it's more likely that the motion will be clockwise. So that's my motion. So friction's going to be opposite way. There's my friction. So now I'm going to find out that TB is going to be larger than TA. No, the other way around. TB is going to be larger than TA. As I start to pull here, I have to overcome the friction. So we'll write now that TB is equal to TA times E to 0.3, and it's pi over 2 for my angle. So that should say what? That TB, this is the same number we had before. Was it 1.6 something?
1.6.
Yeah, so now it says that TB is 1.6 TA. So let's see, I'm going to put this back into my first equation and solve for TA. I could do it a different way, follow the similar procedure. That implies that TA is TB divided by 1.6. So following the same procedure I had before, I go to equation 2, plug in for TA. So I have TB divided by 1.60 plus TB is equal to 20. So what's TB? Let's get 1.6. Plus 1.65. I got 12.31. You guys get that? And if TB is 12.31, then I can go to equation 1, which says that X is equal to TB divided by 20, and I get 0.62 or 0.615. So that now gives me a range. A range of where my 20 Newton load can be. So I can be, from the first part of the problem, 0.38 meters all the way over to 6.15 meters. So if I operate within that range, my platform will not move. So that's, again, that kind of min-max thing. Might be a little too much to ask you to do on the quiz to find both parts, but definitely to find one. Any questions about that? All right.